Today we're going to develop the idea of the double integral, which has this sort of symbolism. Surprise, surprise, it has two integral symbols in it. So if you see this sort of notation, you can read it as the double integral over r of f of x y dA. And it turns out that this is going to represent if f of x y is greater than 0, greater than or equal to 0, this is going to represent the volume between the surface given by the graph of the function f of x, y, and this, what turns out to be a region R in the xy plane, which I've pictured here. And for today, it's going to be a rectangle. So how can we imagine what this would look like in space, at least in part? Well, picture the graph of f as like it's a surface in space, but you can picture it as kind of just a wavy blanket. So maybe something that looks like this, a wavy blanket, and then let me position it so that it's lying in space above our region R. And what we could do then to estimate the volume between R and z equals f of x, y is first off draw a grid of rectangles in R. So I'll just, for the time being, I'll just do a grid, a tic-tac-toe grid, just to keep things simple. And to estimate the volume between this region and z equals f of x, y, we could create a bunch of columns based on these sub-rectangles. I'm just going to try and draw one of these columns for you. So let's say I draw the column corresponding to this sub-rectangle. And I use the height of the function as the height of my column. So let's say I pick a sample point, maybe this point here, and I could use this sample point, plug it in the function to get an idea of how tall my column should be. So let's say it hits the function right there. And then I'll draw the other edge at the same height. And there's the top edge. And this back edge I'll draw at the same height. And then this back edge, same height. Trying to give it some perspective here. Not sure how successful I'm being. And so there's your column. And then the idea is to find the volume of this column, not only this column, but all the other columns we could form with all the other sub-rectangles as bases. And then sub all those volumes together to create an estimate of this double integral. Sound familiar? Yeah, it sounds like a Riemann sum, doesn't it? Yeah, actually, we're going to use double Riemann sums to create the estimate of that volume, and then take the limit and call that limit the double integral. Okay, so let me go to a 2D picture and show you what this region R looks like in 2 dimensions, and we'll make this little definition a bit more precise. Okay, we have an interval on the x-axis that goes from A to B. And let's suppose, for the sake of argument, we have an interval on the y-axis that goes from C to D. And let's suppose that the region that we're integrating over is the rectangle with sides going from A to B and from C to D. So this rectangle formed like so. So now you don't see the function. The function lies above this rectangle that I'm outlining in black here. Okay? The function lies above this rectangle in black. We're looking at it from above. This is the xy plane, and this is our region R that we're referring to previously. Okay. Then how do we find that volume between R and that surface floating above this xy plane? That's what we want to answer. Well, okay, we break up this region R into a grid of subrectangles. How do we define that grid? Well, we first break up the interval from A to B on the x-axis into subintervals, right? A bunch of subintervals. And same with the interval from C to D on the y-axis. Break it up into a bunch of subintervals. And then what we do is we create a grid based on these subintervals. So I'm trying to draw this vertical line right above this grid mark, in case you're wondering what I'm doing. And then horizontal lines corresponding to the grid marks in the subintervals on C to D. And we get this grid of subrectangles in the region that we're calling R in this rectangle. And then, of course, there might be, I put a dot, dot, dot here. There might be a whole lot more rectangles in here. Okay. So we've got this grid of rectangles. Let's focus on one rectangle in particular. Let's suppose that this interval here is the ith subinterval in A to B. I is some counting number. And let's suppose this subinterval right here is the jth subinterval in the interval from C to D, jth subinterval. Then somewhere in here is a box corresponding to the one created by the ith subinterval from the interval from A to B and the jth subinterval from the interval from C to D. And let me pull that box out and blow it up so you can see what I'm talking about. So we'll call this the R sub ij, the ijth box, or sub box if you like. I'm just going to call it the ijth box. Ijth? Okay. So if we keep the dimensions the same for each grid box, we might call the horizontal dimension delta x. Would that sound too crazy to you? No. And the vertical dimension we might call delta y. Assuming they're all constant. They don't have to be, but for the sake of argument, let's say they are. So then what could we say based on the argument that we had previously corresponding to this first picture that I showed you? Well, if we take our sample point to be the upper right-hand corner of the box, then, in other words, this point right here would be x sub I. You could denote it by x sub I and y sub j. Then I think we could say the volume of the ijth column would be, so the volume of the ijth column would be, okay, you take the area of the base, which is just this box, which is delta x, delta y, times an estimate of the height you'd get when you plug in the sample point from the ijth box. So that would be f of x sub I, y sub j, if it's the upper right-hand corner. So, and it really is an approximation, so I really should make this approximately equal to. Okay, based on the conversation we had for the above picture, does this sound reasonable then? Is this okay? All right. So what would we do then? You guys tell me. What would we do to get an estimate of the total volume beneath the big rectangle defined by having sides A to B and C to D? Well, before we even talk about integrals, couldn't we just sum all such volumes over all such little sub-boxes here in the grid? Yeah. Okay, so that you guys can see where I'm going then. So then we could say the total volume. When I say total volume, I'm talking about the total volume between the surface floating out in space above the xy plane and R, that rectangular big box. The total volume would be approximated by summing the volume of all such columns. So how could we represent that? Well, here's the thing. We could use, just for notation, let me do this before I say that. Let's go V sub ij, just for notation. And then that would be approximately equal to. We could use what's called a double sum. So we could, for instance, sum the first column of volumes that we get by running along that column of the grid. And then we could sum the next column. And each column itself, each column of sums in this grid could be considered a sum itself. So you can get what's called a double sum. So you could say V sub ij would be a double sum. And one way to do that would be to first, like I say, sum the volume that you get corresponding to the boxes in this first column. And that would be like your inner sum. So those are indexed by j. So you could sum from j equals 1 to, let's say that there's n subintervals here. So it'd be the sum from j equals 1 to n of f of x sub I, y sub j, delta x, delta y. And then you're going to be summing all such sums going from left to right. And so if there are m subintervals from A to B, and you know that I indexes the subintervals, you could say that you would sum from I equals 1 to m of all such columns of sums. Okay, that sounds confusing, but I'll do an example in a second. And then that double sum would be the approximate volume. And then you can see what's coming here, right? An integral. So what would happen if we made this mesh or this grid of boxes finer and finer? In other words, we introduced more and more intervals. We made m and n bigger. The mesh would become finer and finer, wouldn't it? The boxes would become small. The sub-boxes would become smaller and smaller, right? And you would think that we would get a better estimate of the volume, right? For smaller columns, better estimate, right? Because you could fit more columns underneath the surface. Sound reasonable? So you guys can see where I'm going then. We're going to say, assuming that this limit exists then, that the volume is equal to the limit, as we'll just use this notation, m comma n, both of those go to infinity, of that double sum. The sum from I equals 1 to m of the sum from j equals 1 to n of f of x sub I, y sub j. Delta x, delta y. Which, by the way, we can call delta A. That product delta x times delta y we can call delta A. And then here's the notation we're going to use. Assuming this limit exists, we're going to call it a double integral. Kind of along with the double sum notation, it's a double integral over the region R of f of x, y, this is the notation, dA. So we would call this a double integral of f over R. Double integral of f over r. Assuming that this limit exists in the first place, okay? Now, if f is positive, this represents volume. If f is not, in other words, if f doesn't all lie above the xy plane, then it doesn't represent volume. Okay, we still say, if this limit exists, we still say the integral exists. In this problem, you're given the function values of f of x, y in a table. Some of the function values, I guess. And our region is defined by the interval 2 to 4 on the x-axis and the interval 0 to 4 on the y-axis. I'll draw that for you in a second to show you exactly how that determines your rectangle. And we're asked to find or estimate the function value. Excuse me, we're asked to estimate the double integral of f of x, y dA over that region R. I'm going to do part B for you. I'll let you do part A. So let's get a handle on what this region looks like by drawing it. Okay. So let's see. Just marking my scale marks. 1, 2, 3, 4. Just going by ones. I'm going to do that on both axes. Okay, the interval from 2 to 4. It's critical that you realize the y interval goes from 0 to 4, and then you can actually identify where the lower side of your triangle is. It'll actually be at the height this gives you. So it'll go from 2 to 4, and it will actually be on the x-axis. So this would be the lower side of R. And then vertically it goes from 0 to 4. So your left-hand side of your rectangle looks like this. So R is here. Okay, so then we are asked to estimate the double integral with m equals 2 and n equals 4. M is the number of subintervals on the interval from 2 to 4. So we'll just break the interval from 2 to 4 up into 2 subintervals. N equals 2. So there's the subintervals from 2 to 3 and from 3 to 4, all we need there. And then n equals 4. N refers to the number of subintervals on the interval from 0 to 4. So we'll break the vertical side of the rectangle up like so. And then we'll put in some grid lines corresponding to the endpoints of these subintervals. And we get 8 subrectangles. We break up the region R into 8 subrectangles that way. And then you need to remember that the double integral can be estimated using what we call a double Riemann sum. We can take the double Riemann sum. The first sum would be from I equals 1 to m of the sum of j equals 1 to n. We estimate the function value at some sample points from each of these subrectangles. Doesn't have to be the midpoints. So I'm just going to write sample point, f of the sample point here. And we multiply by delta A. So that's one way to write the Riemann sum. Now we're never going to write it this way, at least in these problems we don't have to. We're actually just going to write out the sum longhand. Okay, so how do we determine our sample points? Well, it tells us. We're going to use the lower left corner of each subrectangle we've created in this grid. So the sample points, here's a lower left corner, that's 2, 0. That's the lower left corner of this subrectangle. We'll go up from there. Here's a left corner, 2, 1, 2, 2, a lower left corner, 2, 3. And then here's the lower left corner of this subrectangle, and then we'll go up from there. That's 3, 0, 3, 1, 3, 2, and 3, 3. So our sample points are just what I said, 2, 0, 2, 1, 2, 2, 2, 3, and then 3, 0, 3, 1, 3, 2, and 3, 3. So what are we going to do? Well, first we need to find delta A, so let's do that. So how do we find delta A? Well, remember what delta A is. Delta A is delta X. It's an area element of one of these subrectangles, delta X times delta Y. How do you find delta X? Well, you take the right endpoint of the x-axis interval, 2 to 4, so you take the 4 minus the 2 and divide by the number of subintervals, just like when finding delta x in Calculus 1. So 4 minus 2 divided by, there's 2 subintervals. So it's b minus a divided by m in this case. And then for delta y, you're going to take d, which is 4, minus c, which is 0. So subtract the endpoints of the interval from 0 to 4. And divide by the number of subintervals, which is 4 in this case. And let me make that look a little better. You get this. And notice both of these are just 1. So delta A in this case is 1, but it won't always be. So when you want to find the Riemann sum, which is your estimate of your integral, you're just going to take delta A, which is 1, times the value you get when you add the function values of all your sample points. So it'd be f of 2, 0, f of 2, 1, add it, and then all the way through to the last sample point plugged into the function to get the height value. So take your delta A times the sum of the function values of all your sample points. And if you go back up and how do you get these values? You just, normally you're given a function, but here you're given a chart. So it's just as easy. F of 2, 0 through f of 2, 3 would be given by these values. And f of 3, 0 through f of 3, 3 would be given by these values. So you're going to be adding 4 plus 3 plus 0 plus whatever that was. I think it's negative 5. Plus 7 plus 8 plus 6 plus 3. And, you know, the 1 doesn't do much in this case. So I can just drop it. 4 plus 3 plus 0 plus a negative 5 minus 5, same thing. Plus 7 plus 8 plus 6 plus 3. If you add all those together, you should get an estimate of 26. And it really is an estimate, so I should make it a little wavy equal sign, a very rough estimate, in fact. There you go.